So welcome back, everybody, and we continue our discussion of trigonometric substitution with an example where things might get a little messier and we have to remember our completing the square. So let's dive into this discussion. All right, so what we're asked to do in this situation is to, again, find the expression, the integral of the square root of x squared plus 4x. So what are we going to use to substitute this? Well, this doesn't match really any of our forms. Remember that we had forms where we had things like x squared plus a squared. And when that happened, it was going to remind us of 1 plus tangent squared. And so our substitution was then going to be a times tangent of theta. If we had something that involved an expression of the form a squared minus x squared, so that was reminding us of 1 minus sine squared. And so that was going to tell us that our substitution was going to be something along the lines of a times the sine of theta. And then finally, if we had something that looked like we had, so an x squared plus a squared minus x squared. And so finally, if we had an x squared minus a squared, what that one was looking like was our secant squared minus 1. And so in that case, we were doing a substitution with x is equal to a times the secant of theta. And so depending on what our expression under the radical was, if it was x squared plus a squared minus x squared minus a squared, we knew what this was going to be. So when we encounter a situation like this, where it's not really one of these forms, we have to do something else to put it into one of these forms. And in that case, what we end up doing, we see this thing underneath the radical, and so we would do a procedure to complete the square to make that happen. And so let's see how we would go about integrating this. Let's see about completing the square and then to see what our integral would look like. So what we have was our integral of the square root of x squared plus 4x dx. Well, our expression x squared plus 4x, we need to convert that. And so the idea was, remember to use this identity. If we had x plus b quantity squared, that thing looked like x squared plus 2bx plus b squared when we multiplied it out. Well, we are missing the constant here, so we put in a new constant. So the idea was that we took our 2b and we said that one was going to be 4. So if 2b was going to be 4, then that tells us that b is going to be 2. And so our new constant, which is b squared, well, we add on that new constant. So we add on a 4, but then to keep things balanced, we also subtract a 4. And so in our first three terms, our x squared plus 4x plus 4 minus 4. Now, those first three terms are a perfect square, and we know they are actually x plus 2 squared, because that's how we designed, that's how we chose b, was so that this thing would look like x plus 2 quantity squared. And so underneath our radical, what we really have here now is something that looks like x plus 2 quantity squared minus 4 dx. And so now if we kind of do maybe an intermediate step of a u substitution, or a u substitution with u being x plus 2, now we can get it into the form that we recognize. So here we had our x squared plus 4x dx. We rewrote that. We completed the inside. And so now that looked like x plus 2 squared minus 4 dx. And so if we do a substitution with u being x plus 2, du then just becomes dx. Then my integral actually becomes the square root of u squared minus 4 and du. So now I do have the form that I need for my trig substitution. So I'm seeing u squared minus 4. So I'm seeing u squared minus 4. And so in that case, I knew that u was going to be, for my u squared minus my a squared. So for that particular constant, so my u being 2 secant of theta, so that my du then becomes, 2 secant of theta tangent of theta d theta. So that in my integral, now what I actually have with this trig substitution, so this thing becomes a 4 secant squared theta minus 4. Du becomes a 2 secant of theta tangent of theta d theta. And the stuff underneath the radical then becomes 4 tangent squared 2 secant of theta tangent of theta d theta. And so taking the square root of everything, I get a 2 tangent of theta. So I get a 2 tangent times 2 secant tangent d theta. So now this gives me an integral of 4 tangent squared theta secant of theta d theta. And so I have a trigonometric integral, and now I apply all of my techniques from the previous section to deal with trigonometric integrals to come down with this kind of expression. Okay, so here, what I can do is I'm seeing that power on tangent being 2, so I can write that tangent as 4 times, using my trig identity, secant squared of theta minus 1 times secant of theta d theta. So if I distribute, now I've got 4 times my integral of secant cubed of theta minus secant of theta d theta. And so for now I have the expression in this form. Now I come back and I recall your recursive formula for integrals of secant. So let's see what that looks like. All right, so reviewing, if you wanted to go back and see where this formula actually comes from, then remember that we obtained this formula by integration by parts. Okay, so that shows up in one of the previous videos, and so if you want to review where that comes from, it's probably not a bad thing to do to refresh your memory on that. But this is the recursive formula that we're going to use. And so if we've got the integral of secant cubed of theta d theta, then that thing is going to be, in this case, n is going to be 1, so that our 2n plus 1 is going to be 3. So if n is going to be 1, then this looks like a 1/2 secant of 2n minus 1, so 2 minus 1 is 1, so secant of theta, tangent of theta, plus 1 over 2 times the integral of, drop the power by 2, so just the integral of secant of, okay. So now what we wanted to evaluate was the integral of secant cubed of theta minus secant of theta d theta. Well, that one will look like, if we split this up, the integral of secant cubed d theta minus the integral of secant of theta. And so if I make those substitutions, what I have for the first one is 1/2 secant of theta tangent of theta plus a 1/2 integral of secant of theta minus the integral of secant of theta. And so combining these last two together, I get my integral of secant cubed minus secant really just being, I don't need this one, so they cancel each other out. And so what I actually have then is 1/2 secant of theta tangent of theta minus 1/2 the integral of secant. And the integral of secant then is, remember that special formula, a minus 1/2 natural log of the absolute value of secant of theta plus tangent of theta plus c. And so this gives us our integral. So now if we kind of bring this all the way back to what our original function was, let's see where we have. So we originally had our integral of the square root of x squared plus 4x dx. We completed the square on that, where we said that u was going to be x plus 2, and that gave us an expression that looked like u squared minus 4 du for that one. Then we did a trig substitution with u being 2 times the secant of theta, and that got us to our integral of 4 tangent squared of theta times secant of theta d theta, to which we then evaluated that to the expression that we just had. So we have a 1/2 secant of theta tangent of theta minus a 1/2 the natural log of the absolute value of secant of theta plus tangent of theta plus our arbitrary constant. Now we kind of want to bring this back to our original variable x, and so we're still thinking of our right triangles for a trig substitution. So if we said that u over 2 was going to be secant of theta, well, secant of theta is going to give us the hypotenuse, u, over the adjacent side, 2, and so that gives us our opposite side of u squared minus 4. Okay. So that if we wanted our secant, that was just going to be u over 2, and so our tangent of theta, opposite over adjacent, is just going to be our square root of u squared minus 4 over 2. But then to bring this back to x, what did we have? That was x was really, u was going to be x plus 2, so I have x plus 2 over 2 for secant, and the square root of x plus 2 squared minus 4 over 2, or x squared plus 4x over 2 for our tangent of theta. So if we take these two expressions, now we can get a final value for our integral. So we had a 1/2 secant of theta tangent of theta minus a 1/2 natural log of secant of theta plus tangent. And so what happens now for our secant of theta, so we have our secant of theta being x plus 2 over 2, tangent of theta being our square root of x squared plus 4x over 2, minus my 1/2 natural log of secant. So secant is going to be my x plus 2 over 2 plus my square root of x squared plus 4x over 2 plus my arbitrary constant. Now, one thing that you could do to maybe clean this up a little bit is you can use your properties of logs. But I can imagine taking out that 1/2, so I've got a 1/8 x plus 2. Oops, I don't have the division. So I've got a 1/2 x plus 2 times the square root of x squared plus 4x minus a 1/2. If I take out that 1/2, so 1/2 times my x plus 2 plus square root of x squared plus 4x plus c, then I can use my properties of logs, where if I had the log of m times n, that was going to be the log of m plus the log of n. So I could separate these out, only take my variables, and my natural log of 1/2 then gets absorbed inside my arbitrary constant. So I could simplify this a little further as a 1/8 x plus 2 square root of x squared plus 4x minus my 1/2 natural log, absolute value, x plus 2 plus square root of x squared plus 4x, and then plus my new arbitrary constant c. So this gets us to a final expression for our integral, and kind of gives us an example of a maybe slightly more involved problem involving trig substitutions where we have to complete the square. So I hope you've enjoyed this, and I will see you guys next time. So my integral of the square root of x squared plus 4x dx then just becomes my 1/8 x plus 2 square root of x squared plus 4x minus my 1/2 natural log absolute value of x plus 2 plus